the introduction. Thank you very much. Thank you to Mita for having me. As Thomas says, I'm going to speak to you tonight on Elastomer asset management. So I think this is a little bit of a hot topic at the moment. Obviously, vaccines are dominating the headlines, and the supply chain and the availability of those. And I think system availability within biopharma now certainly is coming to the fore, and as hopefully we'll see today and decode a little bit. I think Elastomer asset management plays a significant role in that system availability. So without further ado, so yeah, just a very quick highlight in terms of the agenda and the webinar overview. I'd like to explore this topic through the prism of, or through the framework of, a reliability-centric maintenance approach. The reason I want to do that is because we've heard talks in the last number of weeks on some of the tools available to us, for example, through total productive maintenance. So the likes of OEE, OEE2, etc. My feeling on the subject is, obviously, that it's a phenomenal strategy, but I sometimes feel that specific guidelines are the detail for the end user, for the reliability engineer or the maintenance engineer on the ground, can be a little bit scant. So, for example, if we go to the original TPM book, we can see in Pillar 2, which is in relation to setting a predictive strategy or preventative maintenance strategy. The document says establish a thorough system of preventive maintenance for the equipment's entire lifespan, but it doesn't really give the end user much more guidance on that. So personally, where I like reliability-centered maintenance and the approach that John Mowbray has taken there, and I think that fits really neatly into that Pillar 2. So that's how I'm going to structure today's talk, so we can decode a lot of these, a lot of this topic. So RCM for me, look, it's quite a thorough, scientific, robust methodology that will help us understand the problem, which we need to do before we can define the solutions to that problem. Okay, so typically in an RCM framework, we have 7 questions that we need to ask. So that's how I'm going to structure this webinar today. So what are the functions and the desired performance standards of elastomers? What are we looking to achieve here? What is their role? What role do the standards play, or what role don't standards play? In what way can they fail them? We need to understand the failure mechanics, and we need to understand the failure modes. And that's really important, because if we don't understand how they fail, we can never understand how we can prevent that failure from occurring, or how we can predict that failure, what causes these failures. And then what effect do these failures have on my system? Why do I care about these failures? What are the consequences from that? Once we understand the problem and we have decoded the problem in that way, we can then start to look at some maintenance strategy selections, and then obviously work our way into implementation about how we can actually start to get a tackle on, start to tackle the issue. So I have one slide on elastomer science. This is not an elastomer science webinar by any stretch of the imagination, but I just want to throw this up here because, I just want to bring everyone to a very, very basic level. An elastomer is really just an elastic polymer, or an elastic plastic, basically. Okay, so what that means is that when we flex it, or we stretch it, or we move it, that when we do that, it will typically return back to its original shape. Now, if we look at the backbone of an elastomer, or of any piece of plastic, what we have a number of atoms which are joined together in a long chain. Now, if we look at what are called thermoplastic polymers, you can imagine if I basically pulled either end of the strand of that thermoplastic, that once I pull it, it's going to remain in the new shape, or the new form that I've pulled it into. It's not going to return back. And what elastomers do is we have what are called cross links, which are then these additional chemical bonds. And what they do is they act as anchor points. So it means that when I stretch that material, those cross links pull that material back to its original shape. But the key take home message here is that I can't have too many of those. So if I have too many cross links, I then end up with something more similar to what's known as a thermoset polymer. And that, because of what you can almost describe as a net effect of too many cross links, that tends to create quite a rigid and quite a brittle material. So the take home message is that I have cross links, but I don't want too many and I don't want too few. I just want the right amount. And that knowledge is, we'll touch on that a little bit later on when we look at some of the failure mechanics. Okay, so the functions and the desired performance. What do I want my elastomers to achieve, and why are they important in the context of sanitary manufacturing? So elastomer failures in our industry, in the biopharmaceutical industry in particular, can pose a major risk. There are typically thousands of elastomers on any typical site, and ultimately they are the weak link in the hermetic sealing of a system. So, most of the other connections that we have on all of the pipework and all of the vessels, et cetera, tend to be, physical steel connections, welds, etc. And because of the risk associated with them, the maintenance of those soft parts tends to be among the most cost-intensive and time-intensive activities across the reliability programs that we would have on a typical site. And to reinforce this point, if we look at the BPOG survey, which was conducted a number of years ago, we can see that ECOs, again, these are the response from reliability engineers on the ground. They've said that ECOs typically account for 50% of all PM activities. Now, I've seen some, knowing from my own experience that can go as high as 80%. Elastomers drive 20% of all equipment-related deviations. They account for 10% of all corrective maintenance actions. And I suppose the most worrying is that people believe that elastomers present the #1 contamination risk. I don't necessarily follow that line of thinking, which is why I say people believe that, because I think there's a whole plethora of other things that might cause those contaminations. And I think sometimes elastomers can be the smoking gun that people are looking for, although not necessarily responsible. But we'll dive into that a little bit later on. And again, this just reinforces the point. If we look at a typical drug substance facility, what we can see here is, starting from inoculum prep right through to the final product, what we have are multiple systems all physically connected. Again, the integrity of all those connections is depending on the integrity of each and every piece of those elastomers. So be it a gasket or an O-ring or a valve diaphragm, etc. To compound the issue, there's very little failure data available typically, okay? So it can be quite difficult to predict or mean time to failure. It's the where do I start question. The degradation mechanisms are poorly understood generally, so people don't really understand the different types of failure modes and why those failures are occurring. There's little knowledge of what actual process exposures drive degradation. So something that I see a lot is that most people believe, for example, if you look at diaphragms, is that the number of actuations would drive diaphragm degradation and that it will be a good predictor of diaphragm health. Unfortunately, it is a terrible predictor of diaphragm health, and for reasons that we'll explore later on. Of course, we cannot assess the condition of elastomers in situ. We can't visually look at them unless we physically take the system apart, or we can't monitor them via condition-based monitoring. And probably giving away some of the end of the presentation there, but some of my colleagues have asked me, are there modern methods for assessing condition-based monitoring solutions for elastomers? And the answer, unfortunately, at this moment in time is a resounding no. So we have to think of other ways to do that. And of course, as we've seen, elastomer failures can potentially be catastrophic depending on where it occurs. So, okay, I'm not necessarily talking about, maybe certain parts of utilities, but particularly as we start to move downstream and we get post-viral or close to fill finish, there's no redundancy. So if, for example, an elastomer fails, we're talking about a part cost of anywhere from, €10 to €150 roughly, potentially resulting in a batch loss of millions. So there's a massive disparity there between these components that we're trying to keep, reliable, basically, and the drug production systems that they're maintaining the availability of. So one of the key things for me is that elastomers typically have been viewed through the lens of capital expenditure or CapEx and not operational excellence. And I think that has been traditionally an error for the industry. So what I believe is that because of the potential consequences of failures of elastomers, that we have to look at their availability and their reliability as driving the availability of our drug production systems. And so we need to do that via an OpEx focus. And just some ROIs that we have seen based on that kind of focus, based on best practice elastomer asset management strategies, these are some of the results that some of my colleagues on the call might recognize some of these numbers. In one particular site over a 24-month period, we've witnessed a 270% increase in the number of successful batches, a 35% reduction in component failure investigations, a 25% reduction in corrective maintenance actions per batch, and a 12% decrease in contamination events. Another site now, we're very grateful. Our colleagues in Alexia in Dublin have allowed us to use their name and their example tonight in this presentation. They have had continuous uninterrupted system availability for 30 months on cell culture, 25 months on purification, 25 months on harvest, and 24 months on media prep. Again, these are phenomenal results. Of course, it's not just driven by elastomer asset management, but that plays a fundamental key role because they are the weak link. And if you get the weak link right, and you can control the performance of your elastomers, then your system can perform to the best of its ability from there. So that leads us into some of the standards. Now, unfortunately, this is a bit of a vacuum. So end users, your reliability engineers, etc., on the ground exist in a bit of a standards vacuum because the standards governing elastomers are related to purity requirements. Now, obviously, that makes sense in the industry we're in, but unfortunately that there are no actual standards, mandatory standards, that drive reliability requirements. And in my opinion, this has driven lower demands for material reliability and created what you could call a commodity status of elastomers. So what we're trying to do is, lower the price to maintain competitiveness because they are a cost, obviously, but oftentimes that comes at the expense of performance. And if we look at some of the purity requirements, most of you will recognize these. So the FDA 21 CF4 177, what that gives us is basically a general ingredient list called generally recognized as safe. So ingredients that are generally recognized as safe, but specifically for repeated use in food applications. USP 87, or the equivalent ISO, goes a step further, and that's in vitro testing, which determines the biological reactivity of mammalian cell cultures following contact with elastomers. USP 88 then is in vivo testing, which is animal testing essentially of intramuscular implantation, system toxicity, etc. Again, required in relation to biocompatibility, etc., but none of that defines mechanical performance or reliability. This is in direct contrast, for example, to a stainless steel. So if I go out and I want to purchase an American grade 316L or a 14435 grade, German Swiss grade piece of stainless steel, not only are the alloying elements controlled, but the weight percentage of those alloying elements are controlled, and they are controlled explicitly for performance reasons. So, for example, the ferrite content is controlled to control rouge development and proliferation. Sulfur content is controlled for weldability reasons, etc. That doesn't exist for elastomers. Okay, again, to compound this problem, what we can also have is, out of that plethora of ingredients, we can have, a number of different fillers and plasticizers and oils and all sorts of stuff. So what that means is that if I buy, let's say, a plastic from supplier A and a piece of plastic from supplier B, although the name of those, it might be, 2 pieces of EPDM or 2 pieces of silicone or whatever, the actual performance characteristics of those, although they share the same name, are going to vary wildly, or can vary wildly, I should say. So we can get huge differences in relation to the actual hardness of the material, in relation to tensile strengths, in relation to compression set, etc. And then finally, just to make our life that bit more complicated, the performance of the final compound not only depends on all the ingredients, but also how it's manufactured. So has it been extruded or compression molded or injection molded, etc. And again, the take home here is that, an elastomer from supplier A, it doesn't equal an elastomer from supplier B necessarily. Okay. Now, as just a very brief aside, although we have the likes of USP 87 and USP 88, which are, of course, helping us define the biocompatibility, that unfortunately still doesn't protect us 100%. This is a cursory glance at some of the publicly available literature, which has described the per cell growth performance directly as a result of elastomer degradation. Now, a lot of this is coming from single-use technologies, but this is right up to October 2020 that they're still finding these issues. So even the biocompatibility standards, of course, they're not going to be 100%. So we still have a lot of, reliability improvements that we need to make. Okay, so I want to just talk a little bit about the failure modes and the failure mechanics, because I think we need to understand that before we can start talking about solutions. And elastomers fail basically in 3 distinct ways. They can fail to seal, okay, so they're designed to keep the internal environment internal and are designed to keep the external environment on the outside. So if they fail to do that, they lose their sealability. They can fail to be cleanable, okay, so they can lose their cleanability. And they can fail to remain sterile. So typically that would be they're leaching some of their internal ingredients, or they're generating particulates, but we'll have a closer look at exactly what that looks like in a second. So here on the left-hand side, what I can see is some cleanability failures. So what we see is here a deterioration of the surface roughness, and that deterioration of the surface roughness, what that can do is that can obviously hamper my cleaning effectiveness. So, the bugs that are present in my system might attach themselves there, and they might, proliferate and grow quite happily. The same thing here with this kind of deep incision, they might do the same thing there. Again, that's going to hamper the ability for my cleaning and my sanitization procedures to do what they need to do. On the right-hand side, I see a sealability failure, which is essentially here what I meant to have is what's called a external sealing bead, which is a raised lip, which is designed to create that hermetic seal. But I can see that has been completely eroded here. I see this the same picture on the bottom, where this raised lip here is basically completely missing. So this valve would essentially leak. Here what we can see is the results of effective and proper sealability. This is probably quite a dramatic example, but we can see here on a weir type diaphragm valve that the sealing bead in this instance, which on this vendor was actually physically on the elastomer. Some vendors have it on the weir itself, but we can see here that has done its job, and that's what we're obviously trying not to have compromised when I refer to sealability. And sometimes that's not necessarily obvious. Obviously, on some of the likes of our black rubbers and those black materials, it's quite easy to spot that visually with the naked eye. But some of our other materials, like our silicones and our PTFEs, it can be difficult to spot that. So here, PTFE being quite a hard material tends to crush, and we can see that we have this crushing in the center here. So that valve would allow fluid to pass across the top of it. Here we have a gasket that had been leaking, and when we obviously root caused it, we could see that it was as a result of just a small nick on the outside of the sealing bead. So now if we start to think about what we were saying earlier on in relation to some of the performance standards that we're setting ourselves for elastomers, we can see that the integrity of our production systems are depending on a 2, 3, 4 mil strip of rubber, which is quite an extreme situation when you think of it. In relation to cleanability, what I'm referring to basically is that as the surface tends to degrade, 2 things can happen. One is I obviously get greater surface roughness, and that can, physically the bugs that are in my system, dead or alive, can stick to that, and that's, it can begin the process of biofilm growth and initiation, etc. The other thing that can happen is I start to get high free surface energy. So you can think of that almost like static electricity, basically. If you rub a balloon off a woolen jumper, it tends to stick to you. And the same things happen as the material sets degrade. They, regardless of the surface roughness, they can actually just physically attract bugs to stick to them. And often as well, we need to appreciate with cleanability in particular, we often look at the macro surface of a material. So, it looks in decent condition, to the eye. But when we go a little bit further and we zoom into some of these material sets, so what we can see here, for example, on the right-hand side is a gasket. So this is a brand new gasket, and we can see it's, very, very good surface roughness, etc. On the left-hand side here, we see a scanning electron microscope image. So this is, 200 microns here at the scale. So we are quite, zoomed in here. Post-use, that same PTFE surface gasket, we can see that we're starting to have a lot of these induced defects. Again, you wouldn't necessarily spot those with the naked eye. And when we zoom in either further, we can see that the used PTFE surface starts to degrade in this way. Now, I've called out PTFE here, I suppose maybe in particular, all material sets will degrade, but PTFE is is often seen as a bit of a wonder material, which it's not necessarily. All materials have their advantages, and equally they all have their disadvantages in certain applications. Cleanability, again, we see, for example, these kind of cracking or kind of incisions. Again, bugs are going to get in there, do their thing. This is an example, actually, I mentioned at the top of the call that diaphragm actuations are not a good predictor of diaphragm health. This is from a manual valve that I believe had never been actuated. And yet we can see the condition that that's in. And yet we've also seen diaphragms coming out after 30,000 actuations, and they're in very good condition. So something that we'll touch on a little bit later on is that it's not the number of actuations that count, but the process conditions that exist when those actuations are happening. This is a piece of silicone here. We can see, again, I think this is on a bursting disc, and we can see, some melting and deformation. Again, these are areas where bugs can get into that may not necessarily be cleaned. Sterility failures, then finally, this is, as I said, the material is generating particulates, or it's leaching some of its internal oils, and they can go on to physically contaminate our system. We've seen that result of actually, sorry, I'll jump back to this for a moment. This is EPDM, or a black rubber, and one of the things to notice about this is that we see that the material here on the outside is actually in very, very good condition, left and right, but we see that the center of this material is in very poor condition. And that's because EPDM has different reliability based on whether or not it's wetted at the time it's hot. So for example, when that valve is actuated against a hot weir, you tend to get a lot of this degradation. Whereas if it's wetted at the time, you don't get the same level of degradation, which is interesting. PTFE can obviously degrade the same way. It can generate particulates and fray. And how this typically happens is, you see at the top picture here, PTFE can be a permeable material. So when it's, if there are gases and steam, etc., they can actually get into the subsurface layers of the PTFE. And when it, creating essentially a pocket underneath that subsurface layer. So as the system undergoes thermal fluctuations, that subsurface trapped gas will then expand and contract, and it can result in this kind of particulate generation. And we can obviously have a combination of those. So we have here both a cleanability and a sterility failure. So it's obviously going to be very difficult to clean this gasket when it's in service, and it's a sterile failure because it has obviously shed particulates and etc. So just to finish off this phase of the presentation, I'm going to just look at the failure mechanics. So we looked at cross-link density at the top of the talk, and one of the main ways that elastomers degrade is that, due to process exposures in particular, what happens is that we get an increase in cross-link density. So that results in brittleness and stiffness of the material. Or we can get a decrease in cross-link density. So what happens is that the material becomes more flowy, or tends to creep and flow, etc. The material can swell, so due to chemicals and heat, etc. The material can become charred. So we've seen an example of that with the EPDM diaphragm above, particularly under dry heat exposure. And finally, then we have mechanical stressing. So you've input too much tensile or too much compressive stress. But the good news is, from a reliability perspective, 1 to 4 are basically material process interactions that we can try and control through proper strategies. And number 5 tends to be the human installation effort, that or the physical installation of our system. Again, they're all absolutely controllable. So what actually causes all of these things to happen? Well, a number of issues, as I've said: installation issues, process conditions, age. So independent of all other conditions, if I have, all of these materials have a lifespan. For example, EPDM, I think, is a 5 or 6 year lifespan, for example. So it will just naturally degrade sitting on the shelf. Size as well. So is a 1 inch PTFE diaphragm as reliable as a 2 inch PTFE diaphragm from the same supplier? And then just looking then at how this cleanability is compromised in gaskets in particular, just using this as an example. So what we're trying to do is maintain the ideal sealing point, because that's critical to preventing entrapment. So I see here, this is the inside of my pipe on the left-hand side of my diagram. And my ideal sealing point is the junction there where the elastomer is obviously meeting that ferrule. And what I want to do is apply the correct amount of compression so that I don't over crush the material, so it's not sticking into the pipe, but also that I am creating a seal so that fluid cannot find its way up into that, into these areas here where it's not going to be able to be cleaned. So one of the big issues with either swelling or over torquing of gaskets is a gasket intrusion, which I'm sure many of you are familiar with. And we see the consequences of that here on the left-hand side, where we have some of that material, physically sticking into the process flow. So my process flow here is flowing from left to right, and I can see that I tend to get these accumulations upstream and downstream. And what the other issue then is that if I don't torque correctly, I get what's called a recess, and that's where the material is not flush. So I've created this small little hold up area for bacteria, etc. Now, unfortunately, if I over compress a gasket in particular, I can actually have the worst of both worlds, because the gasket will start life off intruding, but then because it's sticking into the process flow, it will become eroded. And then after that, you will then create a recess afterwards. Ultimately, what we're looking for is this nice flush finish. And if I look to the standards in ASME BPE, for example, I can see that the maximum intrusion that I should have is 0.6 mil, and the maximum recess I should have is 0.2 mil. So I don't have a lot of room here for error. And we can see some of the results of excess intrusion here. So what we can see is this compression mark of where the pipe ferrule was. So all of this material would have been sticking into the process flow, and we can see that because of that, all of this material has then been eroded, and we can see that on both pictures, left and right. Now, interestingly, intruded gaskets typically result in 48% more liquid holdup in a pipe. Recessed gaskets can result in 40% more liquid holdup. And I think that's really interesting, because we can have a perfectly designed system with very, perfectly installed drain angles, etc. But just due to either intrusion or recession, we can have significantly more holdup in our system, which is obviously, again, from a contamination perspective, a bit of a no-no. And lastly, then, just in relation to some of the installation effects, gaskets, so certain size gaskets have identical external diameters, but different internal diameters. So what that means is I can put a 1-inch gasket into an 1.5-inch ferrule. And so what I immediately create in those situations, if I'm swapping around those, is that I either create immediately a massive intrusion or a massive recess. And our friends at Pure Transfer have allowed me to use this image, which shows an 1.5-inch gasket in a 1-inch ferrule, and we can immediately see the impact that would have on cleanability and liquid holdup, etc., etc. And finally, then, so a lot of that's kind of installation related, a little bit is related to material swelling due to heat and stuff like that. But then finally, the actual system design itself, so misalignment, particularly angular misalignment, can create the worst of both worlds. So at the top, I'm going to have this over compression, and I'm going to have the intrusion and all the disadvantages that brings. And at the bottom, then I can have a void. And again, so I actually have an intrusion and a recess at the same time. And I can see that effect here. So here, this is a gasket removed where I can see the top, the right-hand side of this gasket would have been, pinched or compressed inside a ferrule, and the left-hand side wouldn't have been. And we can see that the material itself is actually okay. So it has done very well against the process contact, but just as a result of that crushing, that excess compressive force, that it's actually caused this rapid deterioration of the material. Okay, quick recap. We've looked at basically the functions. We've looked at how elastomers fail. We've looked at the failure modes. I'm going to briefly just go through the failure effects and the failure consequences. Then finally, we'll get into some of the solutions. Okay, so the basic consequences of all of these failures: microbiological, endotoxin, chemical, and physical. Okay, what's microbiological? Well, obviously microbes. Not a massive worry necessarily. They're relatively large, and you expect that filtration can probably deal with a lot of them, particularly, as our filters are typically 0.2 micron minimum. Endotoxin is a bit more worrying. It can be difficult to remove by filtration. It can be retained by downstream systems. So a lot of this, for example, will be explicitly related to the loss of sealability. The root cause, as I said, so the sterile sanitary boundary is compromised, or the cleaning cycle can be compromised by the damaged elastomer, allowing process fluids to be retained within the actual elastomer itself. And so if you look at a diaphragm valve, or any valve that has an elastomer front, if that elastomer becomes degraded, some of our process fluid can find its way into the internals of the valve itself, becoming contaminated. Chemical contamination, so damaged elastomers allow fluids to pass. Components of valve bodies, for example, could leak into the process stream. We can leach elastomer ingredients. That typically impacts pH, TOC, cell growth, etc. And then physical contamination. We see here, the result of degraded gaskets and the kind of particulates that they can generate. I'm sure there's many of you on the call who have these headaches. Now, again, not necessarily a massive worry, as depending on where they occur. Obviously, we hope they occur as far upstream as possible so that they can be retained by filters. Okay, finally into solutions, elastomer reliability strategy. We've gone over the problems, we understand the consequences. So what can we do to actually start to control the performance? What do we need to do? So as a quick recap, we know that the consequence of material failure can be significant depending on the location and depending on the material type. So when I say depending on location, I mean, if I lose, for example, cleanability effectiveness on a steam distribution system, do I consider that a failure? Am I necessarily worried about that? Probably not. I am worried about sealability though. And obviously the further I get, post-viral and fill finish, I'm worried about all three failure modes, because there I'm worried about sterility and cleanability and sealability. So failure depends on the area it happens in. So some of those failure modes may not be considered a failure depending on where they occur. And obviously the risks that we have are risks to business and the patient, obviously, but also risks to the environment and risks to health and safety. Materials are not like for like, so we know that now. So we know that the same material from two different suppliers are likely to have different performance characteristics and different reliabilities. And we know that materials degrade primarily through two ways: process exposures and the installation conditions. Now we can control, through correct material and vendor selection and vendor partnerships, we can control a lot of the material side. And then obviously through the likes of staff training, upskilling, and performing system health check reviews, we can start to get a handle on some of the installation conditions. And ultimately, our strategy in relation to elastomer reliability is we want to create a bit of a mouthful here, but we want to create a data-driven, science-based, so based on an understanding of how the materials degrade and how they act, precision maintenance, predictive approach, okay? And what we're trying to do here is drive increased equipment utilization. As I said at the top of the call, we should have a focus on OpEx when we're talking about this issue. And I'm probably going to contradict myself here a little bit, or you may think I'm contradicting myself here a little bit, but I'm going to make a couple of points. And one is that materials don't fail. Okay, materials don't fail. It's the management of the materials that fail. So what I mean by that is that a material is always going to perform to 100% of its ability. The question we need to ask ourselves is, what have I done either in relation to material selection or material installation to basically hamper that ability? So the real question we need to ask ourselves is not why the material failed, but why didn't the material's ability match my performance expectations? And so the number one question that I'm asked, and I'm sure the question probably on a lot of people's lips, is how do I extend my ECO frequencies? Well, the first thing that we need to do before we can extend frequencies is we need to establish consistent material reliability. When we establish consistency in performance and consistency in reliability by understanding a lot of what we've spoken about already on the call, then we can attempt to predict when they will fail. And from there, we can attempt to extend the ECO program. And we have to view this in terms of short-term, medium-term, and long-term goals, depending on where you may be as a site or as a system. The first thing we need to do is have risk mitigation. So we need to put in solutions such as emergency support and spare parts inventory. Our medium-term goals then are risk reduction, so system upgrades, material upgrades, developing in-house SMEs, training them. And then we move into our long-term goals, which is sustainable operations. So, perhaps certified technicians in-house, service agreements, qualified vendors, etc. So as a brief strategy, I'm just going to go through these 6 points quite quickly. And what we want to do is, first thing we want to do is create our controls. Then we want to establish our reliability foundation, conduct our risk analyses, define our cleaning requirements. So what does it mean for something to be cleanable and to be cleaned? Establish, based on that data, a reliability framework, and then implement and manage day to day. So I'm going to go through those 6 points in slightly more detail. Create initial controls site-wide. We need to understand the unique process conditions that we have across utilities, across production, and we need to specify material sets that we believe benchmarking ourselves will be able to perform against those process conditions. We should look at partnering with vendors, for example, specific vendors that we feel, because, elastomer A isn't going to be equal to elastomer B, we have to figure out what material sets are suitable for our specific applications. And then we need to begin the process of staff training and staff upskilling. Establish a reliability foundation. What does that mean? We need to determine how good our current PM program is. So we need to first analyze the parts removed from previous ECOs to see what kind of condition our elastomers are in. If the vendors have reliability data, collect that reliability data. Now, there's not a lot of reliability data out there, unfortunately, and there's no mandatory performance requirements that the vendors have to meet. And we can talk about that later on if you wish in the Q&A. And so often there are huge data gaps, and one of the things that we can do to fill those data gaps is we can do very, short-term, small-scale benchtop testing to, accelerated life testing to fill in some of those data gaps. We can then update material selections based on those results and establish system health walkdowns. Then we conduct our FMECAs, our risk analyses. And we want to do, again, is we want to identify and mitigate the risks in each area of the site. So again, I go back to my 3 failure modes. Are they, again, is cleanability and sterility an issue for me? Do I consider that a failure on a CIP distribution system or a steam distribution system? Potentially not. So I need to estimate the risk associated with those hazards and identify what impact they would have. So each failure of each elastomer would have in each part of my plant. Then, of course, I need to weigh up the risks of physically contaminating the system during the actual physical human interaction, the elastomer change or the ECO activity, and then label my risk and put the risk controls in place. Define my cleaning requirements. So again, what does it mean to be not cleanable? Do I need to support this with small scale studies in relation to, bulk up my cleaning validation studies to figure out exactly what my limit of tolerance is for cleanability of my elastomers? Then with all that data, we can start to establish a rough reliability framework that we can put in place. And again, this is a journey. We need to start somewhere. You're not going to come out of the blocks and have perfect performance, but you need to start the process. And critical to understand is that the predictive strategy should be live. So it means that every time you do maintenance on elastomers, that you're feeding that updated data back into your maintenance strategy to continually optimize it. It's not a document that you write and put on the shelf and create a couple of SOPs and walk away from. It has to be a living, breathing thing. And finally, then, of course, the day-to-day management. We can do a lot day-to-day to ensure the success of this. Conduct ongoing system health check reviews. So, for example, do all of my high-pressure triclamps have washers? Are there any, galled fasteners? Do all of my valves have washers? All these small things that we can do. Develop role, another thing that we can do in terms of system health check reviews is look at drain angles and things like that to make sure that they're consistent, particularly with valves. We can develop, roll out, update specific training content, start to upskill our own people, create those internal SMEs within the organization, implement and update our SOPs, review our Lotto and COE plans to make sure that they're efficient and to make sure that they're targeting the system that we want to target appropriately. And then, as I said, we analyze the parts removed after every maintenance, after every, you might call it an ECO or an SPCO or whatever. And that will allow us to continuously determine the efficacy of our current program, analyze the root causes of failure, and establish, critically, a post-use database of elastomer health. Okay, and then we review our current maintenance schedules and update if appropriate. Now, again, this is a journey. You need to bring people along with you on this journey, okay? So one of the things that you should probably try and do here as well is visualize the journey. So visualize where you are and then visualize, of course, where you're going. So for example, here, if we look at this category here on general maintenance level and we look at strategy, okay, we define this column as chaos and we can say that we have no maintenance strategy. Awareness then, or reactive, we can say, okay, well, we have an informal maintenance strategy, but it's not widely known. We then move into control phase, which is formal maintenance strategy, but no actual implementation plan. We then move into, competence, where we have a formal maintenance strategy with a basic plan. And then finally, we get to the stage where we're at excellence or world class, when we have a comprehensive maintenance strategy based upon the site needs. And there's lots of different metrics that you can use. These are just an example that we've developed with our partners in Pharma Lines. And again, the beautiful thing about, I suppose, this color code and having this as a visual is that we can see as we move through our journey, we can see how we're performing. And again, that can tie into a total predictive maintenance strategy that you're, involving an organization site-wide, and it's, operator care, it's technician care, et cetera, et cetera. People buy into things like this. And then finally, I'm going to finish off by just having a look at some of the state-of-the-art approaches, some of the predictive tools we can use. So I've spoken about a post-use database, and what I mean by a post-use database is what I want to have is I want to be able to have a database which tells me when I remove an elastomer, what the failure mode was, and basically how degraded that elastomer was, okay? So basically the condition of the elastomer when it was removed. And I also want to have the process conditions that elastomer was exposed to when it was in service. So how many hours of steam or how many hours of CIP or buffer or whatever the case might be. If I have a database in that format, the world is my oyster in relation to the analysis tools that I can use. And these are state-of-the-art tools that I can use. I can use an array of predictive tools, so Bayesian Weibull analysis, virtual sensors, Kalman filters, etc. I obviously don't have time to go into any of this now, but just as a very basic example of what a Bayesian Weibull analysis means, it's a Weibull analysis, and the Bayesian piece just means that every time you perform your maintenance, that you're feeding the updated information back into your model so that it updates and becomes the accuracy becomes better over time. And here what we can see on the bottom is we can see, for example, I might start off with a Weibull analysis that looks something like this. So you can see that I have steam here on the x-axis. So for example, this could be elastomer health in a steam distribution system. And what I'm looking at is we have categorized this into 3 different damage states. State 1 would be as good as new. State 3 is a complete failure. And then state 2 is kind of somewhere in the middle. And you can create decision charts and decision trees to define what they are. But the idea here is simply that what I'm doing is I'm creating a predictive tool, not based on time, but based on process exposures to predict the state of my elastomers. Now, what the broken lines here indicate is my confidence bounds. And we can see here that I don't have a lot of confidence in my predictions here. My confidence bounds are quite large. But as I update this model over time, what we'll see is that the predictions themselves become more accurate, and the confidence bounds, i.e. my confidence in my predictions, become better and better over time. And this is the place that I want to get my elastomer strategy to, because now I have consistency of material reliability. I have reduced the special cause variation due to installation issues or human errors, et cetera, et cetera. And now I can see what the true performance of that material set is. And when I get to that phase, then I can make decisions on whether I want to partner with different vendors or use different material sets or, implement different design strategies on my system, etc. But this gives us the data to be able to do that. And the final point I want to make is that what we're not doing here, we're not replacing a risk-based approach to elastomer asset management. What we're trying to do here is inform the risk-based approach. So we're trying to increase and improve the accuracy of our risk assessments. That's ultimately what we're trying to do. So that's the end of my talk. Thank you very, very much for listening. I hope that wasn't too laborious for you all to sit through. There's some of my contact details, of course. If anyone wants to get in touch with me offline, please feel free to do so. Thank you very, very much.
Thanks, Aaron. That was brilliant. Very comprehensive presentation. We have lots of questions coming in, so I'll give you a chance to digest some of these. So the first question is from Andrew Wood, and he's asking, do you find that the failure is an instant problem, or is it a direct result of continued use? If it is continued use, is there any way to predict when that failure will happen?
Yeah, so so the answer, unfortunately, is both. So yes, it can be instantaneous, and yes, it can also be as a result of continued use. So I think I probably touched on that at the end of the presentation, at least I hope I did, which is that what we need to do is the first thing we need to do is establish consistency in our performance. How we do that is we need to eradicate the special cause variation. So the sudden rupture, no material set suddenly ruptures unless it's really put into process fluids that it just doesn't belong in, or it was installed incorrectly. So I've basically, if you can eradicate or massively reduce your human errors in the first instance, that will drive down most of those instantaneous failures, and then we get to the stage where we get where we can start to make those predictions. I hope that answers the question, Andrew.
Okay, yeah, perfect. And the next question then is in from Paul Phelan. So the act of removing a failed elastomer can often cause the damage, or sorry, can often damage it on removal. Have you any tricks to differentiate between the damage caused by actually removing the failed elastomer as to the damage present at the time of failure?
A really, really good question. Yeah, you can. Again, like it's probably a little bit of a skilled eye, but one of the keys is looking at the elastomer as a whole. Okay, so like typically, if you have something that like damage done by removal, it tends to be fairly obvious. You tend to have kind of scratch marks of say screwdrivers or something like that on it, but the actual material itself tends to be in relatively good nick. It will be very difficult to show you without maybe showing you some pictures. I don't have them with me, but generally, yes, you can tell the difference. Yes.
Okay, perfect. And just the next question also from Paul, do you examine and record the state of every single elastomer that you remove?
No, you do it by exception. So basically, like, you can do every single one, and we often do, but I suppose what you can do is basically have, acid in good condition. Okay, and you can, obviously have a cursory glance at it and see what kind of condition it's in. And if it is in a good condition, then you can essentially set that aside. And anything that maybe has a feature on it that you're a little bit concerned with, you put that to another side, and they're the ones that you do a little bit more investigation on, if that makes sense. But you would certainly, cursory have a look at everything. Definitely, yeah.
Perfect. The next question in is from Shane O'Neill, and he's complimenting a great presentation. The question is, if the install is 100% correct, what factors dictate the frequency of the change out?
Brilliant question. Yeah. So then that's exactly when we're into our, let's say, predictive phase. Okay. So now we're into actually seeing what the performance of the material can actually do. So once we eliminate human errors, that's when we start to reduce a lot of the variability, typically, particularly if we have control over the material set. So, we're not using, say, a piece of silicone from 7 different suppliers. But if we have control over that, then, the types of strategies that we can start to use then are the likes of our Weibull analyses, etc., that I spoke about at the end of the call.
Okay, perfect. And the next question in then is from Cormac McCarthy. So Cormac's talking about the process conditions around the closing of a hot valve weir, and it can cause premature failure of diaphragms. From his own experience, he's seen that most of the diaphragms don't fail across the actual weir, across the sealing point. So if the diaphragm is cracking or failing on one side of the diaphragm, is it more likely due to overexposure to the medium heat or steam rather than the closing of the hot weir?
Yeah, so it is, particularly if it's very obviously just on one side. That's very much a process interaction. So I would agree with you completely. You don't like that failure mode that I showed up on the slide isn't typical. I just wanted to point out that against dry heat, elastomers can fail in that way. So a very quick example of that would be if you had a valve block or a valve manifold and you had 6 or 7 valves on it, and there was part of that valve block was being SIP'd, you would have some diaphragms on within that manifold that are being wetted and some diaphragms that aren't being wetted, but the whole manifold is going to heat up. So the valve diaphragms that are not wetted but basically being compressed against that hot weir, they're going to degrade quicker than the ones that are wetted. It's not a usual occurrence. I just wanted to bring it out that it does happen
Okay,
because it's one of the failed modes.
perfect.
But definitely, yeah, you can very easily differentiate left and right as he's suggesting. Yes.
Brilliant, thanks. The next question is in from David Cantwell, and there's two questions to this. So it's the first one: what do you perceive as being the future of elastomer technology from a materials perspective?
Wow. Okay, that's a good question. For me, what I hope is that, again, we go back to the regulations and the oversight. I would hope to see more input there. Unfortunately, a lot of the performance standards at the moment are non-mandatory, and even the ones that are not that do exist are largely written by the vendors themselves. So it's the vendors themselves defining the performance requirements of seals, which, it's not, the end users aren't really engaged in that process, which has its obvious disadvantages. So what I would like to see is basically more studies, more focus put on the ingredients and the methods of production to enhance performance, not just biocompatibility. That's where I see it going in the short term. To be honest with you, if your question is in relation to kind of condition-based monitoring solutions, I don't see anything on the horizon personally. Nothing that will actually deliver true, kind of revolutionary value, if that makes sense.
Okay. And so the next one then is from Richard Hall, and Richard asked, do SCRI-IS offer vendor choice advice to help customers choose valves with better elastomers?
Yes. Short answer to that question.
I think Richard will take you up on your details possibly after that on that one. And the next question is in from Ger Clark, and Ger asked, how have you ensured consistency during install of elastomers by a large maintenance team?
Yeah, great. Yeah, great question, Jer. For me, it's training, and it's ongoing training, and it's making sure the guys understand what they're actually being trained in. So it's not a question of read and understand the SOP. It's not a question of, I've done a half day 4 years ago. It's about actually, actively training and making sure the guys have that skill set. And so that might be, consistent refreshers, and also then maybe consistent review of performance. So if you are doing appropriate data collection, I mean, again, we have people here who are interacting with our system. If you have someone who's going in to weld 2 pieces of pipe together, you would expect that they are skilled and experienced. And yet the failure of a weld would have the same consequence as the failure of an elastomer, but we don't demand the same level of skill for people installing elastomers, which is quite strange. So what we should be doing is having enough data that we know who interacted with our system and when they interacted with our system. So we know that it was Joe Bloggs went that tri-clamp 4, and he did it in October. And that's not used to beat people over the head with. That's just used to understand if you have, maybe consistent technicians who maybe aren't, they might be doing excessive install or whatever the case might be. And then you can target those individuals with more training or more understanding. But you have to understand who is interacting with your system and make sure they're skilled, basically.
Perfect. The next question in is from Ronan Murphy, and Ronan asks, is there any published data for expected service lives on typical duties, e.g. ambient purified water with weekly sanitizations?
Not in the public domain, and anything that does exist that you have to buy for considerable amounts of money isn't really fit for purpose, because it's not done on a statistical basis, and it's not done on a representative sample of different process exposures. So unfortunately, the answer there is no. So like what we can do is obviously, help, clients benchmark themselves globally. Now, we're in a very fortunate position. We obviously interact with these day to day. So we have a post-use database that we've collected thousands of data points. So we can help clients, benchmark their performance levels. But unfortunately, there's nothing available in the public domain at this time.
Okay. The next question in is from Thorsten Fisher, and they're asking, do you find that the users have a good process models at hand to allow to describe process exposures of a specific valve?
No, is the short answer to that question. I don't. What I find is that unfortunately people are still operating on strategies that maybe existed 10, 15 years ago, and they're still trying to work with those same models, which are a little bit outdated, and I don't believe meet the current needs of the industry.
Okay, and we have another one in from Nigel Ruddle. He asks, what is your opinion of an elastomer versus PTFE? A difficult one. So hard to quantify, I suppose.
Yeah, like it's not really. Look, I go back to the point I made in terms of every material has its advantage and disadvantage. So there's a great mathematical theorem called the no free lunch theorem, and it basically proves mathematically that anything that has an advantage in one aspect will have a disadvantage in another aspect. So PTFE is a fantastic seal against a lot of different chemicals and quite thermally stable, but PTFE is very poor under typically under thermal fluctuation conditions. So if you have a lot of kind of ambient to hot to cold, etc., PTFE tends to perform quite poorly, and that's where an elastomer can perform quite well. So it very, very much depends on the specific application.
Perfect. So we have 2 questions left. We'll finish up with these 2. So the next question is from Jerry Larkin, and Jerry's asking, for reciprocating application that has little process variance, is there a number of cycles a good life or age predictor?
That's a great question. In that instance, I would say yes. Yes, I would potentially. I'd need to obviously know a little bit more about the application, but you see, it would depend on the system design. So, do you have just purely process interaction effects, or do you have maybe, I don't know, physical rubbing of the seal? And, there'd be a couple of questions I'd need to ask back in order to get a full understanding. But I would imagine, yes, that it will be it will be more appropriate.
Okay, no, perfect. That's brilliant, Darren. We're just coming up to 8 o'clock, so we'll bring things to a finish. Just on behalf of everyone at META, thanks very much for coming on and giving a really, really good, comprehensive presentation. It's been very, very good. So thank you very much for that.